Well, welcome back to another BC lesson here tonight, and we're going to continue our discussion of determining whether a series converges or diverges. And tonight we're going to introduce you to the integral test. And again, it's just as we said, it's used to determine whether a series converges or diverges, the age-old question that we've been battling for a couple of weeks now. Don't panic if this little picture is too blurry. Don't worry, we'll go into it in greater detail. But I just want to do a little intro here. Basically, the integral test says we've got some prerequisites. F's got to be continuous. It also has to be decreasing, and it has to consist of only positive terms. So, for instance, we just saw the alternating series test, and we wouldn't be allowed to use the integral test on an alternating series because it contains some negative terms. But basically what's happening is you might have a function here, and notice it's above the x-axis, so it's positive, it's continuous, and it's decreasing. And basically, if the improper integral happens to converge, then the series is also guaranteed to converge. Or vice versa, if the improper integral diverged, then the series would also diverge. So they're kind of married together. Whatever one of them does, the other one does as well. Real quick here, and I want to emphasize this part before we move on, is that we're only, the series, or this test only applies to series with positive terms. If there was any negative terms in that series, we would not be allowed to use the integral test. All right, so for our notebook, we'll refer to this as Theorem 9.1, and we'll get in those prerequisites. We'll say, first of all, F has to be, we'll start off with positive, and it also has to be continuous. And it also has to be decreasing, we'll say for all values of x starting with 1, or for all values of n starting with 1. It's got to be decreasing from that point forward. If those three things are true, then we're going to say then the series and the integral, and I'll throw some bounds on there. We'll say this one starts at n equals 1 to infinity. This one starts at x equals 1 to infinity, a little dx to make it official. Either both of them are going to converge or both of them are going to diverge. In other words, they are married together. Whatever one does, the other will do. Now, here's a great disclaimer to put in. If they do converge, okay, which that'll happen quite often, they don't necessarily converge to the same value. In other words, they measure slightly different things. The series is just adding up individual terms where n's only allowed to be an integer. And then whereas the integral is calculating the area underneath the curve. Now both numbers will be very small, but they won't necessarily be the same number. So just because your integral ends up converging to a 2 doesn't mean that the sum of the series is also a 2. So for our first example, we're going to try to apply the integral test to determine whether this series converges or not. And the series I'd like to start with goes from 1 to infinity, and it's the fraction n over the quantity n squared plus 1. Okay, so let's go through our prerequisites really quick. We'll just kind of do a checklist off to the side. First of all, will this one always be positive? And I would say, knowing that n's going to start with 1 and continue on, my numerator is always positive and my denominator is always positive, so yes, those fractions will always be positive. Number 2, we'll say, is it continuous? And notice I looked at the denominator, and my denominator would never equal 0. So I'm going to say check, yes, this one's continuous. And number 3, is it decreasing? And basically, as long as we've got small over large, which we do here in this case, that'll guarantee that this function decreases. So we've got all the prerequisites satisfied. So now I'm going to dig in, and I'm going to evaluate the integral that goes from 1 to infinity, and I'm going to change all my n's to an x. And it's a subtle detail, but it's important because when we use n's, we're saying the domain's only whole numbers, positive whole numbers, whereas when I use x, I'm saying the domain's all real numbers. And so I'm going to rewrite this improper integral using a limit. So we're going the integral from 1 to b. And while I'm doing that, I'm going to start to use a u sub to finish off this integral. I'll change colors real quick for the u sub. Let u equal the denominator. So there's some really good review of some integrating techniques from earlier in the year. And we'll divide over the 2x. Let's see here. We'll create some more space. So we've got the limit as b approaches infinity. x over u times du over 2x. Great news here, cancel the x's, so it's exclusively in terms of u. We'll factor out the coefficient. My antiderivative is going to be the natural log of u. And let's see here. What I'm going to do is I'm going to go back and I'm going to rewrite my antiderivative in terms of x right off the bat so that I don't have to change my bounds here. And now we'll plug in the bounds. So I've got the natural log of b squared plus 1 minus the natural log of 1 plus 1. And what's happening here is as we evaluate that first term, this term right here is approaching infinity. Therefore, the integral diverges. And if the integral diverges, then the series is also guaranteed to diverge because of that. So there's example number 1. Our second example, ironically, is going to look almost identical to the first one with a subtle change that's going to have a huge impact on the antiderivative. And I'd be really impressed if you wanted to hit the pause button right now and we're feeling semi-confident with this test and you want to go ahead and try it right now on your own, I'd really encourage you to do so. And just because I think if you can get this antiderivative all by yourself, you'll feel, you should feel very proud and pat yourself on the back. So again, our prerequisites, number 1, are the terms always positive? It looks like my numerator is always positive, my denominator is always positive because of that squared sign in the adding, so check off that one. Is the function continuous? Ask yourself, will the denominator ever equal 0? And I would say that's never would equal 0, again, because of the plus sign. And number 3, is this function decreasing? And again, we've got small over large, so that pretty much guarantees that it's going to decrease for all positive whole numbers, and we're good to go. So I'm going to set up my integral again, changing all the n's to an x to recognize the slight change in domain. And we'll rewrite our improper integral in terms of a limit. B approaches infinity. And I'm not going to do, well, I guess I should say, I'm going to do a u sub, but it's a very slight one. Letting u equal the denominator like we did in the last example is not going to get the job done. I wouldn't be able to cancel all my x's like we had hoped to. And this actually fits one of our very special rules. It's the arctan rule. And if you recall, we said if you have du over a squared plus u squared, the antiderivative is going to be 1 over a arctan of u over a plus c was that general antiderivative. So I'm going to apply that one here. And what I'm going to do is I'm going to say my a is a 1 and my u is an x, which implies that my du is going to be a dx. So we're good to go. And we'll rewrite this limit. And so the antiderivative of that term right there is going to be 1 over 1 arctan of x over 1 with bounds from 1 to b. So let's plug in the upper bound first. Arctangent of b minus the arctangent of 1. And here's an example. You know, maybe off to the side of your paper you want to draw yourself a little sketch of arctan. And this is the one that's got horizontal asymptotes at pi over 2 and negative pi over 2. And it increases so subtly within those asymptotes. And what you'll notice is that as b approaches infinity, the arctangent curve approaches a height of pi over 2. And the arctangent of 1 is simply pi over 4. So by the time I subtract those numbers, I get pi over 4. So here's what we're saying. The integral converges to pi over 4, which then guarantees that the series will also converge. The kicker is I don't know what it converges to. It won't necessarily converge to pi over 4. In fact, it's highly unlikely that it would. But I do know that the sum of that series approaches a finite number, and therefore the series converges. I wanted to kind of finish the night off with looking at some examples where the integral test may not apply. So I brought up some series that might violate those 3 prerequisites we said that we've got to meet before we can use the integral test. And as we look at example number 1, we ask ourselves, are the terms within this series always positive? And the answer to that is definitely no, because we've got an alternating series, which is fine by us. In fact, that's great news. I would prefer to use the alternating series test any day of the week And we notice that perhaps you remember that this is actually the alternating harmonic series right here. And we've proven other ways that that one's going to converge. But the bottom line is we cannot use the integral test on a series that possesses some negative terms. Example number 2 here, what you'll notice here is this particular, whoops, grabbed the wrong one. Notice the cosine of n here in the numerator. What that's going to do is it's going to, because cosine of n oscillates, and certainly sometimes cosine yields positive values, sometimes it yields negative values. What's going to happen is this particular series is not always decreasing. Okay, it's not always decreasing, and because of that, we would say that the integral test does not apply because of the oscillation that takes place right here in the numerator. And we'll use another test later on in the year called the comparison test to handle that better, just as easy as any of the others. So hopefully you feel pretty good about the integral test. It's largely dependent on your confidence level with an improper integral and being able to evaluate those. And if you feel good about evaluating an improper integral, you're going to be in great shape tomorrow. All right?